could I just ask, what do you think is an acid? And what is a base? What do you understand to be an acid or a base?
I actually don't know how to.
So you probably don't know the definition of an acid, and I guess that's part of what this module is about. And before this, we really haven't defined what an acid is. So can you tell me what you know about acids then?
I actually don't know.
Oh, you don't know anything about acids.
No.
So can you tell me what their pH is? Do you know how they taste?
No.
Oh, okay. Sure. Well, there are a few things that, and if you only started studying in year 10, maybe you've either forgotten or you maybe didn't pay attention, but there are some general sort of properties. So we're going to be looking mostly at properties of acids and bases. This might be a revision for you, but it sounds like it might not be. Essentially, we're going to be saying that acids generally, taste
Sour?
Yeah. So do you just think everyday life? What sort of things taste sour to you?
Lemon?
Yep. Any other examples?
I don't know, soy sauce or anything?
Oh, soy sauce is not really sour, it's more salty. But so if you stick with more sour, then lemon is a good example. Another example, like what sort of thing do people add to add a sour taste? If you wanted to add, like, soy sauce gives you a salty taste, right? But what sort of sauce could you add to make it sour?
I don't know.
如果你想要加个，就是如果不是酱油，你想加其他酱，然后你想要就是加了之后呢，你吃起来有酸酸的，哪种酱是酸的呢？
不知道。
醋啊。So vinegar is also an acid. So lemon is acidic. Vinegar, so those are very classic examples of things that are acidic, right? There's obviously a lot of things that are acidic, but those are two very common examples. So one thing is that acids will taste sour, but another thing is that they will basically turn blue litmus red. And these are things that you might have come across in science in previous years. And we also say that acids are corrosive.
Like, what is the character after blue? Like, term
Litmus.
blue?
Litmus is a type of, so in junior science, litmus is a thing that we put in acids or bases, and it changes color. So if you put this thing in acid, it will, if it was not red to start with, it will become red. And if it, if you put it in a base, it will turn red litmus blue.
Like, how to spell, like, Litm. Oh, sure.
And at this point, if you're not clear about this, it might be helpful for me to point out that thing can be acidic and it can be basic, and these are sort of opposites of each other. Okay?
Yeah.
But actually, there is also something in between. Do you know what goes in between?
No.
So, okay, so we can classify, substances either as acidic or basic. Those are the sort of,
like neutral
and neutral, correct. So basically we've got your sort of columns here. All right. And so neutral, there is going to be no change to your litmus. So if you take this thing litmus and you basically, put it, litmus can change color. So if you put it into an acid, it will become red. It could be red already, in which case it will stay red. But the fact is, if you put it in an acid, it will become red if it wasn't red already. Now, if you put it in neutral, it will just not change color. If it's blue, it will stay blue. If it's red, it will stay red. If you put it in a base, if it was blue, it will stay blue. But if it was red, it will turn blue.
Yeah.
So these are sort of the general properties of an acid or base, which, you don't seem to be familiar with. But so acids are what we call corrosive. So you can think of that as it reacts with inorganic things. So that's the general idea. Whereas bases are what's called caustic, and they react more with organic substances in comparison. Now they both can react with the other as well, but that's the sort of general idea. So corrosive means that it reacts more with sort of inorganic substances. Base reacts more with sort of organic substances. So think of organic things like sort of food and fats. Think inorganic like sort of metals, rocks. Does that make sense?
Yeah.
And so therefore, we have this idea that we've got substances which can either classify as neutral, so there's nothing in particular, or acidic, which tastes sour and turn blue litmus red and are corrosive, or bases which taste bitter and are caustic and will turn red litmus blue. Okay.
Yeah.
And one way we tell them apart is we say, we can use things like litmus, which changed color, to tell them if it's an acid or a base. But another way that you may have come across before, have you ever heard of pH before?
I know some value.
All right, so if it's neutral, what's the value of the pH?
7.
If it's acidic?
Below 7.
If it's basic?
Above 7.
Yeah. So that's the sort of thing that we probably expect you more or less to know, before year 12. All right. There's something called a pH scale, which we will do in more detail in this module. Not today, but we will talk about pH in more detail. And we're basically saying that if pH is 7, it's neutral. If it's less than 7, it's acidic. If it's more than 7, it's basic. We can use litmus to kind of tell where it is. And if it's on this sort of scale, then it tastes sour and it's corrosive and sort of reacts with these things. We'll talk more about that on the next page. Bases, they taste bitter and react more with sort of fats and so forth, which is why we use basic things to often clean sort of toilets and ovens, because if you've got food, that's what you want to react with to get rid of it, right? You generally don't use an acid to clean an oven because instead it will react with the oven and damage your oven and not get rid of the food as much. Does that make sense?
Yeah.
So let's firstly talk about acids. And let's talk about reactions of acid. Do you know any common examples of reactions of acids?
Let me see. Sulfuric acid.
Those are examples of acids, but do you know of any reactions of acids?
I couldn't recall. Like, there's nothing coming to my mind.
All right, sure. In which case, let me just run through it. It sounds like this is not a topic that you know very well. So perhaps it might be more helpful if I run through things directly. So let's start with some examples. So examples of acids. You've got a few common ones that you definitely should know and you should hopefully recognize. So we've got HCl. Now note for an acid, this is always AQ for the situations you come across. That means it's an aqueous solution. It's not liquid. It's not gas. It's not solid. It needs to be in aqueous solution for it to be an acid. Okay?
Yeah.
And this is called hydrochloric acid. You've got nitric acid. You've got sulfuric acid. So those are probably the three most common acids that you really need to sort of know at the moment. We will be talking about more of them. But there are, I suppose, other ones. So I'll just give you a few examples just to give you an idea. So you've got carbonic acid, which is like H2CO3. And you've also got, for example, phosphoric acid, which is H3PO4. So those are some examples of acids. And we can give you some examples of classic bases as well. So bases are generally, you might have something like sodium hydroxide. You might have, for example, potassium hydroxide. You could have, for example, magnesium hydroxide. And so on and so on and so on. Yeah.
Yeah.
Does that make sense?
Yeah.
So in our sort of simple thing sort of here, do you notice anything common about all your acids?
They have the presence of hydrogen.
Right. So we will be talking about more of this in the coming weeks. But one thing we might notice is, in our examples here anyway, acids have hydrogen. And we'll talk more about that in the coming weeks. Do you notice anything about your bases so far?
Like, we got the presence of OH.
Right. So here, bases have hydroxide. So we will now start talking about sort of acid reactions. So there are probably three key reactions of acids that I would expect you to sort of know. Number one is called neutralization. Does that remind you of anything? Like, do you know what neutralization is now, or not clear?
I know, like, is neutralized just mean like the same number of protons, same number of neutrons? Or
Not in this situation, no. So firstly, it will be the number of protons and electrons if you're talking about neutralization. And that would be, sort of physics and talking about the charges. But in this context, as a reaction, no, neutralization has specific meaning. And so if you don't know what we're talking about, then it's clear that you're not clear on that. So neutralization is the name of the reaction between an acid and a base. So if you have a neutralization reaction, you're saying that acid plus base and then we'll, in our name of this reaction anyway, we'll give you salt plus water. So this is reaction number 1.
Yeah.
Okay. Do you understand what salt means?
I know that in Chinese, but you mean like in chemistry?
Yes.
I know it's an ionic compound.
Yeah, that's what it is. But to be clear, salt does not mean sodium chloride. So to be clear, the salt here, I'm not talking about, you know, table salt. I don't mean the salt you eat. I don't mean, you know, I don't mean like, you know, NaCl. I mean any ionic compound.
Yeah.
So as an example, we could have HCl plus NaOH. Now this will become NaCl plus H2O. And that's your acid plus base gives you salt plus water. In this case, the salt is NaCl.
Yeah.
But I could easily change the acid to something else. And I can change the base to something else. And then I'm going to get, well, K2SO4 plus 2H2O. Does that make sense?
Yeah.
So that's your neutralization. That's firstly number 1. All right.
Yeah.
I'll quickly run through both the other reactions with you first, and then we will talk about these in a bit more detail.
Yeah.
So reaction number 2 is your acid plus metal. Now, to be clear, your metal needs to be a sufficiently reactive metal. What we mean by sufficiently reactive depends on stuff you've done in year 11. For the moment, we won't get into the details of that, but in year 11, you studied sort of in module 3 how metals can differ in reactivity, and you've done redox equations, hopefully about, you know, a bit less than a year ago. So those things, the metal needs to be sufficiently reactive. Not every metal will react, right?
Yeah.
And the acid needs to be what's called a displacement acid. You probably don't need to worry too much about the acid type of thing. But generally, assuming you've got an acid that is normal and one that you're likely to come across, and a metal that is sufficiently reactive, then an acid plus metal will give you your salt plus hydrogen gas. So an example could be HCl plus, let's say, zinc, which will give you a salt plus hydrogen gas.
Yeah.
So as you can see, this salt is an ionic compound, but it's not NaCl. This salt here is an ionic compound, but it's not NaCl at all. So the salt, as we said, it just refers to any ionic compound.
Yeah.
So now let's go through the third reaction. So the third reaction is when you have an acid plus a carbonate. And this will give you a salt plus carbon dioxide plus water. So these are the general things that general reactions you need to understand. An acid can react with a base, an acid can react with a metal, an acid can react with a carbonate.
Please go back to the previous slide. Right.
We will go back to it at some point, but sure, take a look at it now.
Yeah.
We will be writing more on these slides. So in this case, let me take an example such as HCl again. And let me react it with a carbon, such as calcium carbonate. And when this reacts, I'm going to get calcium chloride plus carbon dioxide plus water. Are you done with this page?
Yeah.
All right. So now these are, so I guess as a summary, I'll put it quickly on the next page, but we'll go back on the, so we're saying that general ideas of reactions with acid is that it could, 1, react with a base, 2, it could react with a metal, and 3, it could react with a carbonate. Those are the 3 sort of general things we kind of expect you to know at this point. And the equations are, you know, what we've outlined on the previous pages. And this is an example. Acid plus base gives you salt plus water. And that's, you know, take any acid that we've given here under this situation and any base that we've given here, and we can do that. And so as part of your homework, I want you to, you know, try writing these acids with these bases. So you've got 5 times 3, 15 possibilities. Go and, you know, do those questions and write them out. Okay?
Yeah.
Now, the thing is, I don't want to just write the equation like this. I kind of want to sort of know what's going on. Do you know how to write an ionic equation?
Yeah, I think so.
You do? All right. Can you write out the ionic equation for hydrochloric acid plus sodium hydroxide? Can you work out what the net ionic equation is? I want you to work out the net ionic equation for both of these.
But like, for example, like I want to get an NaCl. Did I just take Na and take a charge and plus like Cl take a charge? Right.
So I'll show you, I'll tell you what, I'll do it for this one and then you do it for this one. Okay?
Oh yeah.
So I'll do this, the first one in class. So let's work out the ionic equation for, the concept is the same, and I will be doing them for all 3 equations, right? Now, one thing you probably want you to understand is for an acid in aqueous solution, it forms hydrogen ions. So in other words, your HCl aqueous is actually forming H plus Cl minus ions. And these are things that we'll go into more and more detail in this module, but that's one thing I want you to understand. Okay, so HCl is, your acid is forming H plus ions.
Yeah.
And if you've got an H plus ion, you've got a Cl minus ion. So therefore, when I have HCl aqueous plus NaOH aqueous to give me NaCl aqueous plus H2O, that's my neutralization reaction from earlier, the whole equation. But I now want to work towards a net ionic equation. So I need to think about, is HCl aqueous, is that ionic? When I have hydrochloric acid, does it exist in terms of ions?
No.
And the answer for an acid is yes, it is existing as hydrogen and chloride ions in solution. So what that means is you've got H plus Cl minus. Because it's an acid, it forms ions in solution, and so it's ionic. Does that make sense, or you sound a bit confused?
No, it makes sense.
Okay. You understand the difference between being ionic and not ionic?
I'm not sure.
So what we're basically saying is if something was not ionic, and when you dissolve it in water, it will stay as HCl and HCl and HCl. And they will be bonded covalently, right?
Yeah.
But the thing, and you know, if you have an ionic substance like NaOH, so NaOH, when it's a solid, is going to be formed of Na plus and OH minus in this sort of form. And this continues forever. But if you dissolve it in water, what basically happens is that they separate from each other. I'll just draw 4 of them. They do their own thing. So when an ionic substance dissolves in water, the ions just separate. Okay. And there are details about ion dipole attractions and so on that you might have learned in year 11 that we're kind of ignoring here right now. But the point is, when you take sodium hydroxide, which is an ionic substance, and you dissolve it in water, the ions just separate. So these NaOH in solution exist as sodium ions and hydroxide ions in solution. Does that make sense?
Yeah.
Now, what makes hydrogen chloride a little bit different than sodium hydroxide is that if you have hydrogen chloride, it's actually a covalent molecule. So hydrogen chloride gas is a molecule. This is not ionic. So you can see that these are molecules, and this is a covalent bond, and this is not ionic. But the thing is, if you were to dissolve HCl in water, and this is not true for everything, but it is true for things that, like HCl and that become acid. If you dissolve it in water, it will then become an H plus ion and a Cl minus ion. And this is therefore hydrochloric acid. This is not hydrochloric acid. This is just hydrogen chloride gas. But once you dissolve it in water, it will become ions. And that's what makes it an acid. Does that make sense?
Yeah, so like all acids are ionic.
Not necessarily to start with, but when they are in the acid form, then in short, yes, at least for what we're talking about right now.
Yeah.
So, in aqueous solution, then they will form H plus ions. And yes, but I'm not saying that ionic to start with. I'm saying when they become an acid, when you dissolve them in water, then yes, they will exist in ionic form as free ions.
Yeah.
But let me stress, HCl, not as an acid, as the gas, is not ionic.
Yeah.
So I would not say HCl is ionic. I would not say that. I would say HCl is not ionic. It's a covalent molecular substance. But when you dissolve it in water, it will ionize and become ions. Do you see the difference?
Yeah.
Whereas I will say that sodium hydroxide is ionic because it's ionic anyway.
Yeah.
And when you dissolve it in water, then the ions separate. Okay?
Yeah.
Now, so sodium chloride is like this, except instead of OH, you get chloride. So it will become, you know, Na plus Cl minus. It's just ions floating around. But water is not ionic, so I write it as H2O, like that. Understand?
Yeah.
Any questions with that so far?
It's okay.
Now, you can see that there's sodium on the left and sodium on the right, yes?
Yeah.
So they can just cancel. Because you start with it, you end with it, it didn't really do anything. What else do you see on the left and the right?
Cl.
Right, so chloride and chloride are both on the left and right. Again, it didn't really do anything. So these here are called spectator ions. They didn't really do anything. So we can remove them. They didn't really do anything. They just happened to be the one that, this happened to accompany the H plus, and this happened to accompany the OH minus, but they didn't really actually react. They stuck around at the start and they were there at the end. They didn't really do anything.
Yeah.
So your net ionic equation, let me rub this out. So your net ionic equation is the one without any spectator ions. So your net ionic equation is just H plus OH minus to give you H2O. In other words, this is the net ionic equation for this neutralization reaction.
Yeah.
Does that make sense?
Yeah.
All right. Could you run through the same steps and try and work out the net ionic equation for this reaction?
Is it just H plus aqueous plus OH minus aqueous equals to H2O?
Liquid. Now, do you
Liquid.
notice anything?
Balance it?
No, not balance
No.
it. Do you notice anything about it? Do you notice anything about that equation? So
No.
what was the net ionic equation of the one I worked out?
Oh, they're the same?
Yeah. Do you think there'll be any different if we sort of change it?
No.
No. So what we're really saying is that for any um, neutralization reaction, for any base, acid or base, then the net ionic equation is what you said. H plus OH minus to give you H2O. That's actually what's happening. So you can see probably, and that's the power of the net ionic equation, is to get rid of the things that are irrelevant and that don't matter and focus on the parts that do matter. So can you see that the acid is what gives you the H plus? The base is what gives you the OH minus. And it doesn't really matter what the acid is paired with or what the base is paired with.
So can I quickly go get the charger?
Sure. Then, but yeah, I'm just saying, then it's just the net ionic equation. That's really important. Yep. All right, go grab the charger. So what we're really saying then is that this is the, ionic equation for neutralization for any acid or base. Now, I want you to think about this. This is coming from the acid. So any acid gives you the H plus, like doesn't matter what the anion is. And this comes from the base. It doesn't matter what the cation is. So it's really that the H plus from an acid is reacting with the hydroxide from a base to give you this. And if that is what is happening, are you able to work out if this is an exothermic or an endothermic reaction?
Oh, because I don't know. Usually, what given like is like the reaction is exothermic or endothermic. Like depends on
Yeah,
like.
you often are, but do you understand from your year 11 work how to tell if a reaction is endothermic or exothermic?
I know it's like exothermic, it's like heat releasing and endothermic.
Yes, but where does the heat come from? So if you're releasing heat, where does that heat come from?
I'm not sure.
So in a very simplistic way, it comes from your chemical potential energy, right? So basically your chemicals are releasing the energy that they had, but that energy and you should have done this in module 4 last year when you did enthalpy and so forth, but that chemical potential energy is as a result of the bonds. So basically you have what's called bond energy, and when you break apart a bond, you
Like,
need energy.
yeah.
When you form a bond, you will release energy. Okay?
Yeah.
And whether or not the overall result of a chemical reaction is endothermic or exothermic depends on how much energy you needed to break all the bonds compared to how much energy was released when you made the bonds. Okay, so you got to look at it before and after. What it cost you to break the bond and what you got out of it when you made the bonds. So here's the thing though. In this reaction here, you've got an H plus and an OH minus, right?
Yeah.
And our H plus is positive, right?
Yeah.
OH minus is negative, right?
Yeah.
When they meet to form water, are they forming a bond or are they breaking a bond? Are
The
these
break
are these things forming a bond or breaking a bond?
the breaking up.
No, they're not actually. They're joining together to form one thing.
But do they just break bonds first and then to reform new bonds?
Well, you don't really need to break the OH bond, but sure, even if you did, you're making that bond anyway. What I'm really getting at is these two will just join together.
Yeah.
And you don't need to help them because one is positive and one is negative.
Like it happens spontaneously.
Which means it wants to happen, which means it will release, like it will form that bond, and you don't need to make it happen. You don't need to provide energy to make that happen. And when they form this bond, they will release energy because it's a formation of a bond.
Yeah.
So therefore, a neutralization reaction is therefore exothermic. And that's one thing you need to know as well. a neutralization, which is a reaction between an acid and a base, will give you a salt plus water. If you're looking only at the net ionic equation, then it's H plus plus OH minus gives you H2O, and that will be exothermic.
Yeah.
Okay, now we can do the same thing for acid plus metal and acid plus carbonate. I want you to get the ionic equations, the net ionic equations of each one. Do you think that's something you can do?
Yeah, I'll try.
Right, give it a go.
Like when I cancel things out, I just like H plus aqueous to hydrogen.
Not quite, because this is so I think you might have made a mistake. This zinc is ionic, so this is Zn2 plus. So let me show you the steps. So you should have got H plus. So firstly, you need to balance, so this needs to be a 2 here, all right? And so
Yeah.
well, you'll have 2H plus 2Cl minus plus zinc solid is not ionic, so it's just zinc. And zinc chloride is an ionic in aqueous, so it's zinc 2 plus 2Cl minus plus H2 gas.
Right.
And you can see the chlorides cancel, which then gives you a 2H plus zinc solid to give you zinc 2 plus H2 gas. And this indeed is the net ionic equation for my example here. As you've probably already realized, the net ionic equation is basically going to look similar. It's basically going to be a 2H plus your metal. That could be 1 plus or 2 plus, but you just change it accordingly. So let me imagine it's 2 plus, whatever metal that is. And that would generally be your equation, net ionic equation.
Yeah.
Okay. So acid plus carbonate, similarly, you're going to have 2H plus 2Cl minus. Now, calcium carbonate is ionic, but it's a solid. So formally, when we write an ionic equation, we should write that together. Formally, we should write it together, okay? And that's going to be calcium 2 plus aqueous plus 2 chloride aqueous plus CO2 gas plus H2O. Now, you can see that the 2Cl minus cancels. Now, formally, calcium carbonate should not be separated, but for the purposes of my demonstration here, you understand that calcium carbonate is made up of calcium ion and carbonate ion. And so imagine it was soluble and that these two will cancel. So your net ionic equation for any acid plus carbonate is actually 2H plus CO3 minus. It's just the reaction of the acid, which is the H plus, with the carbonate ion, which is CO3 minus, to give you CO2 gas plus H2O liquid.
So actually, can I just assume like calcium carbonate is actually soluble? I just assume.
It's not that we're actually assuming it. It's more that whether it's soluble or not, for the purpose that I'm trying to demonstrate here, it doesn't actually matter in the sense that it is just going to be reacting with the carbonate ion. The cation doesn't matter.
Yeah.
And so these are your three basic acid reactions: acid with a base, acid with a metal, and acid with a carbonate, with essentially your net ionic equations looking something like this. And those are, you can see how we got those through our examples there. And a key thing you need to note as well is the neutralization. This is called neutralization, and it's exothermic, which you can express as delta H is negative.